Beer's law. All right, Beer's law states that absorbance is equal to A, B, C. So A times B times C, where A is the absorptivity constant, which should be different for each analyte, but can be determined it's a constant, stays the same. B would be the length of the light path, and then that would be determined with each analyzer and will be very specific to that analyzer. So that can be, so A and B can be constants already determined, and therefore there's a direct relationship between the absorbance and the concentration of a certain analyte. And so this can be illustrated here with the graph. So if you were to take 4 samples of this analyte, usually 4 standards of known concentrations, and let's say there are concentrations here from 1, 2, 3, and 4 going up in concentration, and you would get a reading of the absorbance as you run them. And so let's say the sample 1 reads right around here at around 0.1, sample 2 is going to read around 0.2, you plot it. Sample 3 is going to be reading around 0.3, and sample 4 is going to run around 0.4. So in general, this is a linear relationship, and so then a line can be drawn, and this can become a function and calculate it. Then when you run a sample, your sample itself, you run it and you get an absorbance measurements. And if your absorbance was here at 0.35, you could calculate, as it would right here, about what the concentration would be, which would probably be right there in the middle somewhere. My graph's not very precise. And so that's how Beer's law works in spectrophotometry.